Hey guys, so today we're going to be doing the first page of the Unit 1B notes. So this is lesson 1B.1 and it's called the Squeeze Theorem. Okay, so the Squeeze Theorem says that if g of x is less than or equal to f of x, which is then less than or equal to h of x for all x not equal to c in some interval about c, and that the limit as x approaches c of both g of x and h of x is equal to the same value L, then that means that the limit as x approaches c of f of x also has to equal L. So in other words, if g is less than f, if g is below f on the graph, and if h is above f on the graph, visualize it. And if g and h then both come to the same value at a certain point, their limits approach the same value, then that means that f has to approach the same limit. So what's on top and what's on bottom are coming to a point, basically. And you're saying that what's in the middle has to come to the same point. Okay? So in other words, if g and h both go to L, that means that f is literally getting squeezed between them and also has to approach L. Okay, so here's an example. Usually with the squeeze theorem, you're going to have examples where it's a trig function times some other function. So here we're doing the limit as x approaches 0 of x squared times the sine of 1 over x. And we want to show that that equals 0. Okay. So the thing about sine, if you think about the basic graph of just sine of x, is that the maximum y value that it reaches is 1. It goes up to 1 and then it comes back down. And then the minimum value that it reaches is -1. So if we use that maximum of 1 and we say, well, the sine at most is going to be 1, then that sine times x squared has to be less than or equal to 1 times x squared. In other words, it might be less than 1 times x squared because of the sine, but at the most, the sine is just going to be 1 at the most. And at the least, it's going to be -1. So we know that x squared times the sine of 1 over x has to be greater than or equal to -1 times x squared. Okay, so we're thinking about the most that the sine part could be and the least that the sine part could be. So that means that the negative x squared has to be less than or equal to x squared times the sine of 1 over x, which then is also less than or equal to positive x squared. Okay. Well, let's look at the limit of each of those functions as x approaches 0. Again, we can't substitute the 0 into the one with trig in the middle because that would put a 0 in a denominator, and that's bad times. But we can substitute 0 into negative x squared, and we can substitute a 0 into just x squared. Both of those, of course, just give us 0. Hey, look, now our limit is getting squeezed between 0 and 0, which are the same value. So that's what I mean when I say the bottom and the top, in this case the negative x squared and the positive x squared, have to go to the same value. And in this case, that's 0. So by the squeeze theorem, that means that the limit as x approaches 0 of x squared times the sine of 1 over x has to also equal 0. So take a moment and get out your graphing calculator. I want you to enter these three functions. I've got it down here at the bottom of the screen. So we're doing negative x squared and positive x squared. That's our top and our bottom. And then x squared times the sine of 1 over x. That's the one that we're squeezing between the other two. Also on the bottom right of the screen here, you'll see I've got the window settings. So make sure you hit the window key and enter those in because we're zooming in really small on the graph and I want you to be able to see the same thing. So once you're all set up and ready to go with that, then unpause the video and proceed. This is what you should be seeing on your calculator screen. So on top, on my screen here, it's in blue. Yours may be different, but that's just the graph of y equals x squared, the basic parabola. And then we have y equals negative x squared on the bottom, which is just the parabola reflected, of course. And then the fun stuff in the middle is that x squared times sine of 1 over x. And you can see on the graph here what I mean when I say it's literally being squeezed between those two functions. for all x. But what we're concerned about with the theorem is the point where the top and the bottom parabolas meet at the origin. So the limit as x approaches 0 for x squared is equal to 0. The y value is also 0 at that point. Same thing for the bottom parabola. You plug in 0 for x, you get out 0 for y. So the squeeze theorem is saying the top and the bottom are meeting at a point, which means that the limit at that point for the one in the middle, our fun squiggly friend here, has to go to that same value too. Okay? So that's the idea of the squeeze theorem. We're kind of finding that point right in the middle of the two. All right, now, the rest of this you don't have to put in your notes. You flip to the next page, you'll see it's going to be a totally different lesson. So the rest of this I just want you to watch, okay? This is a painful proof. Please don't bother writing this down. I mean, you know, you really want to, I guess you could, but this is not something you're going to have to do on the AP exam. You just have to recognize when it is being used, okay? You're just going to have to be able to look at it and recognize that we're using the squeeze theorem. So don't freak out about how difficult this proof is about to be. Okay, that having been said, let's dive in. This is one of our TTKs. You've seen this before, and at the time I said just take my word for it. And now that we know the squeeze theorem, I can show you why this works. The limit as x approaches 0 of 1 minus cosine x all over x equals 0. We can't do this algebraically, of course, because it puts a 0 in the denominator. But if we start with sine and tangent of theta, sine of theta has to be less than theta, which is less than tangent of theta. If we take the reciprocal of all of those, it also flips our inequality sign too. So we put 1 over sine and 1 over theta, and then 1 over tangent. Since tangent is sine over cosine, the reciprocal would be cosine over sine, aka cotangent. Okay, then we're going to take our numerators and we're going to multiply everything by 1 times cosine theta. Okay. And then the next step here, all that has happened is that we've put it in, we've switched the order so that it's from least to greatest. Okay, so we just move the left to the right and notice that the inequality signs flipped with them. And now we're taking the limit of all three functions as theta approaches 0. Now this is going to take a little bit of work, so we're going to just focus on the limit on the left first. Okay, so we can't plug the 0 into that because sine 0 in the denominator would just be 0. So we have to get rid of that sine 0 with a little bit of algebraic and trigonometric manipulation. So with that 1 minus cosine theta on top, we're going to multiply top and bottom of the fraction by the conjugate of that, 1 plus cosine theta. Because conjugates use the difference of squares, and on top that becomes 1 minus cosine squared theta. Okay, well, 1 minus cosine squared is just sine squared, because sine squared plus cosine squared equals 1, so if you subtract the cosine from both sides, you would just get sine squared. And on top, we just have a product. And on bottom, we have a product, which means that we can cancel one of the signs on top with the sign on the bottom. That's what we wanted. Remember from the beginning of this part, we were saying the sine of theta in the bottom is the problem factor that we're trying to get rid of. Now we just got rid of it, which means that now we have something where we can substitute. We can take this theta approaching 0, substitute in the 0, and cosine 0 is 1, so that's fine, and we just get that the whole thing goes to 0. So that's the limit of the function on the left, or on the bottom on the graph. Now let's focus on the one on the right. It's going to take a very similar approach and get a very similar result. Spoilers. Okay, so 1 minus cosine theta, we're going to do the same thing. We're going to multiply top and bottom by the conjugate so that we get 1 minus cosine squared on top, because 1 minus cosine squared is sine squared. Then we can cancel some sines. Sine over 1 plus cosine. Now we can substitute. Hey, look, it's also equal to 0. So back to the squeeze theorem. If the lesser limit and the greater limit are both 0, that means that the limit getting squeezed between them in the middle also has to be approaching 0. So therefore, by the squeeze theorem, the limit as x approaches 0 of 1 minus cosine x over x has to equal 0. So now you see the origin of this TTK, and you know why I said we'd come back to it later, because that origin is kind of messy. So again, this is not something you're going to have to prove. You just need to know this TTK, because again, it's not something you can solve by substitution. And if ever you don't have that, you don't have access to the graphing calculator on a problem that requires this identity, that's why this is a TTK, because this one you just have to know, and you can't do it algebraically easily. All right, so you've got the worksheet. That's it for the notes. So you've got a worksheet. Most of it is just analytic limit review, because you can never have too much practice with that. The two at the bottom both involve a product of a trig function times another function. So I want you to do those while looking at the example we did in today's notes with x squared times sine of 1 over x, because that'll kind of be your template and your guide. So think about the min and max of trig functions, sine and cosine, okay, -1 and +1, and use that to figure out what you're squeezing between for 7 and 8 on the worksheet today. All right, and we will go over that tomorrow. Thanks for watching.